Welcome to the Flexcom software tutorials. These videos provide a practical overview of how to use the software and take you step by step through sample model creation and analysis. This worked example considers a flexible riser in steep wave configuration. It is a very straightforward example and illustrates basic model building principles. The example consists of a static analysis of the riser, followed by a dynamic analysis of the riser subject to wave loading and first-order vessel motions. To create a new project, select New Project from the File menu. You will then be presented with options for defining a project name and a project folder. It is advised that you use a project folder other than the worked example basic folder in the Flexcom installation directory. This will ensure that you do not overwrite the original files and will allow you to use the original files as references to verify your own files should you experience any problems. Once the project is created, you need to add the first keyword file to the project. To add a keyword file, select New File from the File menu. Select a blank file template which uses the metric unit system. Then enter the name K1 SWR static .keyxm and create an empty keyword file. We will begin by modeling a line in the keyword editor. The line modeling feature provides an automatic mesh creation facility which expedites the model creation process. The riser, including the lower catenary, buoyant section, and upper catenary, are modeled using a single line running all the way from the seabed to the base of the ship. The line is called riser and is assigned a length of 430 meters. Its start and end locations are called lower end and upper end. The meshing algorithm automatically generates a finite element discretization based on user-specified guidelines. In this example, a minimum element length of 1 meter and a maximum element length of 5 meters are specified. The structural properties of the riser vary along its length due to the different components, so it is necessary to define a number of subsections in terms of distances along the line. The subsections are called lower catenary from 0 meters to 80 meters, buoyant section from 80 meters to 210 meters, and upper catenary from 210 meters to 430 meters. The Modelview provides a live structure preview facility available during model building. It allows you to rotate and pan the viewpoint, to zoom in and out, and has many other useful display features, such as node and element numbering, nodal coordinates, seabed topography, and water surface profile. Beginner or inexperienced users may prefer to use the table editor. Data is entered in tabular format with the various rows and columns clearly labeled. A new table for defining element sets is now created in the table editor. This is added by right-clicking in the table editor and selecting Add Feature. The features are grouped together into logical categories and subcategories as appropriate. Flexcom uses the concept of element sets to define the physical properties of the finite element model. Groups of similar elements are logically combined into named element sets. Properties are then assigned on an element set-by-set basis. As the lower catenary and upper catenary have identical structural properties, a single element set called bare section is created to group both of these sections together. Flexcom provides two different formats for specifying structural geometric properties. These are termed the flexible riser format and the rigid riser format. In this example, the steep wave riser's structural properties are specified in the flexible riser format, including bending stiffness, torsional stiffness, axial stiffness, mass per unit length, inner diameter, drag diameter, and buoyancy diameter. Note that the structural properties of the buoyant section are identical to those of the bare section, with the exception of the buoyancy diameter, which is larger due to the presence of buoyancy foam. The presence of the buoyancy material gives the flexible riser its distinctive steep wave configuration. The simplest hydrodynamic property specification in Flexcom is that of constant hydrodynamic coefficients that remain the same throughout an analysis. 5 coefficients are specified to model drag, added mass, and inertial loading. For simplicity, all elements in this example are assigned the same hydrodynamic coefficients. Flexcom traditionally groups together 4 parameters required to provide the minimum environment specification, including the analysis water depth, the density of seawater, and the gravitational constant. Flexcom requires an effective outside diameter in order to compute stresses, such as bending stress or von Mises stress. For properties assigned using the flexible riser format, the default outer diameter is assumed equal to the drag diameter. In this example, the default value is suitable for the bare section, but is incorrect for the buoyant section. So the star properties keyword is used to explicitly assign the correct outer diameter for the purpose of stress computations. You can resize the table and keyword editors by clicking on the center bar, holding the mouse button, and then dragging the mouse vertically. This allows you to expand your preferred editor for increased usability. Flexcom has a range of options for modeling seabed topographies. This model uses a simple flat rigid seabed. Note that keyword entries may be auto-completed by pressing the Tab key. Two sets of inputs are required to completely define the response of a floating vessel to the ambient wave field. The first set defines the vessel's initial position. The vessel in this model is located at x is equal to 305 meters, y is equal to 120 meters, and z is equal to 0 meters, and has an initial yaw orientation of 50 degrees with respect to the global y-axis. The second set of inputs relates to the vessel RAO data. As this data may be quite extensive, it is typically stored in a separate file, which is simply referenced by the main keyword file. The file with RAO data already exists in the worked example basic folder and is named K1 SWR-RAO.INCX. This should be copied into the folder for this project. Flexcom offers a range of standard vessel profiles to provide enhanced visual appeal. You may choose to insert an FPSO, semi-sub, drillship, etc., or even define your own customized vessel. In this example, an FPSO profile is added with dimensions of 55 meters by 170 meters by 30 meters. The COP input is used to adjust the vessel image position slightly if required. The type of analysis to be performed must be specified in each load case section. In this example, a static analysis is firstly performed. Flexcom presents a comprehensive range of options to fully describe the constraints which are applied to the finite element model. The most widely used boundary conditions are constant, which are time invariant, and vessel, which are used to apply vessel motions. In this example, the base of the riser is fixed at the seabed, and the upper end is attached to the vessel. Note that relevant node labels were created automatically by the lines facility during model building and may be referenced when defining boundary conditions. It is important to define meaningful names in the lines keyword, as these names may be referenced subsequently in other keywords. In this example, the relevant node labels stemming from the lines keyword are called upper end and lower end. These names are clearly defined and easy to remember. Note also that when referencing node labels, you must enclose them in curly brackets, as shown on screen. Flexcom provides a comprehensive internal fluid modeling capability. In this example, the riser is filled with oil, as evident from its mass density. The level above mudline input is set equal to the riser elevation. Flexcom uses this input to determine whether elements are filled with fluid, and also to compute the hydrostatic pressure. An initial static analysis is typically run from 0 to 1 second using a single fixed time step, and this standard approach is adopted for this example. Database post-processing is the most powerful and widely used post-processing facility in Flexcom. In this example, the post-processing requests are specified before the analysis begins, via the standard output option. For every element set referenced, Flexcom produces outputs of effective tension, resultant bending moment, and von Wie's stress for that set. Once the specification of the data is complete, you should save the keyword file and run the analysis. When a run is in progress, you can monitor its status via the Analysis Status area. The progress bar is naturally more beneficial for longer dynamic analysis. You can view the analysis results using the plotting facility. Plot files have the extension .mplot T. Here are snapshot plots of effective tension, resultant bending moment, and von Mies stress. The presence of waves, whether regular or random, requires you to perform a dynamic analysis. Select New File from the File menu. Select a blank file template which uses the metric unit system. Then name the file K1-SWR-dynamic.keyxm. You may define constant parameters within a keyword file and reference these parameters when defining input variables. If you choose to define any such parameter, their definitions must appear at the beginning of the keyword file, under the Preprocessor section. For the purpose of this example, a single regular wave will be examined. A new parameter called period is defined and assigned a value of 10 seconds. The type of analysis to be performed must be specified in each load case section. In this example, a dynamic analysis is required. In this example, a regular wave with period of 10 seconds and amplitude of 5 meters is created. The wave direction is set equal to -130 degrees, aligned with the local vessel surge axis. Appropriate time variables are computed based on the regular wave period. The dynamic analysis runs for 5 wave periods, with the loads ramped on over the first wave period. A fixed time step equal to 5% of the wave period is used. Note that any references to predefined parameters or any mathematical equations must be enclosed in square brackets as shown on screen. The restart facility allows us to specify that a particular analysis is to be restarted from a previous run. This allows us to build up the full dynamic solution in stages. In a restart, the structure configuration at the end of the preceding analysis becomes the starting configuration for the restart. Database post-processing is the most powerful and widely used post-processing facility in Flexcom. For this analysis, the statistics output category is used. A plot of the maximum-minimum envelopes of effective tension and bending moment is requested. The statistic output feature is calculated over the last 2 wave periods in this example. Flexcom excludes any values before this time. The units entry explicitly specifies what units are to be assigned to the plot. This entry is optional, and if omitted, Flexcom simply assigns suitable base units. For example, the base unit of force in the metric system is the Newton. However, as effective tension is normally presented in kilonewtons, kilonewtons is explicitly specified here. Kilonewton meters is explicitly specified as the desired unit for bending moment. Once the specification of the dynamic data is complete, you should save the keyword file and run the analysis. When a run is in progress, you can monitor its status via the Analysis Status area. You can view the analysis results using the plotting facility. Plot files have the extension .mplt. The plotting tool provides several options for zooming in and out. The quickest is probably to simply use the mouse scroll wheel. Alternatively, you can hold the Control key while dragging the mouse, allowing you to select a particular zoom area. You can pan the view by holding down the left mouse button, and the grid and axis move in accordance with the mouse movements. Plot tooltips are very useful. The feature is enabled via the Toggle Tooltips button. When the mouse cursor is hovered over the plot, the tooltip displays additional information about the data point, such as its location within the finite element model. You can also use the Toggle Crosshair tooltip to connect points on the plot with their corresponding axis values. After a dynamic simulation, the model view provides a playback option to examine the structural response of the riser subject to wave loading and first-order vessel motions. The video can be played at different speed settings, and it can also be stepped through frame by frame for a more detailed inspection. The model may be rotated by left-clicking on the screen, holding the mouse button, and then dragging the mouse. The area of interest should first be placed in the center of the screen using the arrow keys, or panning with the mouse. In order to ensure a smooth rotation, you should click near one of the screen edges and drag the mouse in a straight line towards the other side of the screen. Flexcom uses color contouring to graphically display element forces, such as effective tension or bending moment, and this provides the engineer with an intuitive visual representation of the finite element results. The model view window can be split into as many as 4 panes, each with an independent view. Each view has an independent camera position and independent draw options. You can pan the model using the arrow keys on your keyboard. You can also pan by right-clicking on the screen, holding the mouse button, and then dragging the mouse. During panning or zooming mouse operations, a red circle appears in the center of the screen. This is a useful reference point either for centering an object of interest or rotating the viewpoint around it. This concludes the first Flexcom tutorial video. A simple worked example based on a steep wave riser configuration. Now that you have mastered the basics, you should proceed to the second tutorial video. This is a more complex example which considers a freestanding hybrid riser arrangement. In addition to the fundamental concepts introduced in this tutorial, the next video also includes some more advanced topics, such as pipe-in-pipe, keyword parameterization, summary post-processing, summary post-processing collation, code checking, and video creation. If you would like further information on Flexcom, please send an email to software@mcskenny.com or visit our website. Thank you for watching.